Okay, good day, everyone. So we will get started. Do you have any question before we get started? Okay, so I finished grading some of your test number 2, and then I'll try to finish by Friday. And on Friday, if you have any question about let's say you didn't get a good score on the project number 4, number 5, talk to me, right? I won't do any lecture on Friday. I'll focus on helping you improve your Excel project 4 and 5. And also, hopefully I finish grading by Friday. So if you have any question on your test number 2, you can also talk to me on Friday, right? On an individual basis. And actually, I post all the lecture PowerPoint for the remaining of the semester. So we have 5 more sessions to cover. All right, so let's get to that. So last chapter, chapter 4 is mainly about the probabilities. So let's look at it. So let's go to section 4.1. Let's take a look at some basic concepts of probabilities. You can open the PowerPoint. Okay. Let's open it. And that's all saying, right? There's only 2 sure things in life, right? Death and taxes. This exactly explains what the boundary of the probability is, actually. And probability is a term we utilize to measure the certainty, right? We use that to measure the certainty.
Professor, we can't see your screen.
I probably didn't share that yet. Okay, let me share that. How about now? It's good?
Yep.
Okay, very good. Thanks for the reminder. So measure certainty of any event in life, right? So certainty, or another word you can say uncertainty. Either something is certain or uncertain, right? And then anything in between are possible. So this is most fundamental concept of probability. Of course, you probably have your own understanding of probability. They're all good. It probably come from the real life experience. Actually, probability was developed via the real life. So back in the time, ancient times, all those mathematicians, they start developing this concept of probability based on their daily life. Like when they have a coin, they flip a coin, they figure out the probability of getting head or tail, and a lot of theory was developed through that, real life experience. Okay, and one of the important fundamental term we use is called rare event rule for inferential statistics. Rare event rule is like if under a certain assumption, right, the probability of a particular observed event is extremely small, we conclude that assumption is probably not correct. And think about all those lottery advertisements. You probably watch some of those lottery advertisements, right? What's your feeling about this lottery advertisement? What's your intuitive feeling? Anybody want to share your opinion on this lottery or Mega Million, advertisement? So my impression about those lottery, like advertisement is they're giving you impression that you have a chance to win a lottery, right? You get a good chance. You have a good chance. Of winning the lottery game, right? So you could be a millionaire, billionaire instantly winning the game. But in reality, once we finish this chapter, you will understand how to calculate the probability of probability of winning for any lottery game or Mega Million or any like gambling activities. in reality, the probability of winning lottery gain is extremely small. So this lottery advertisement, or all those advertisements actually try to impose a very bad assumption, right? Meaning everybody have a good chance of winning the game, but in reality, the probability of winning is very, very small. So probability of winning is like almost equivalent to impossible of winning the game. Okay. Although you do see somebody win the game, right? But think about it, maybe tens of millions of people buy lottery ticket, but only 1 or 2 person win. So you can think about it, the probability of winning is extremely low. So this is what we call a rare event rule, meaning sometimes if you doubt any assumptions about probability, you should do your own investigation, look into that carefully, and come up with your own objective, conclusion about the assumption. Right? So usually statistics. So statistics it's one of the major branches of mathematics. Our department also offer these statistics courses, right, to help you understand, what's going on in real life in terms of analysis part. So statisticians use a rare event rule for inferential statistics. And if you later on, if you study MA 222 or MA 321, and this could be a very useful, assumption for you to have. Okay, so now this session, in session 4.1, we're gonna have 3 approaches to finding the probability of an event, right? And I'll get to each one of these assumptions and also approaches. So the most important objective of this section is learn how to interpret probability values. So using this P representing the probability, and we'll try to interpret this value, right? Based on different index and different and also intrinsic meaning of each probability values. Okay, so probability start with the event. So think about very simple event like flip a coin. If you have a coin, a quarter or die, flip it. Remember, you're gonna have 2 outcomes, right? Either get a head or tail. Okay, another event could be rolling a dice, right? 6 faces, assuming it's 6 faces. So your possible outcome is either getting 1, getting 2, getting 3, getting a 4, getting a 5, getting a 6. Okay. So this is the event. Example of event, flip a coin, could be rolling a dice. So first example, second example, to help you visualize what is actually an event. So event is any collection of results, outcomes. So when you flip a coin, you're bound to have 2 outcomes, right? Either a head or tail. Either one of them will show up. Similarly, if you roll a dice, you are bound to have one of these numbers, right? 1 through 6. And the outcome not certain, meaning you are not certain about the outcome, meaning all these possible outcomes usually are equally likely, right? Okay. A simple event is an outcome or event that cannot be further broken down into simpler components. For example, flip coin, get a head, right? This is a simple event. Flip coin, getting a head. Definitely a simple event. Or rolling a dice, getting a number 6, getting a 6, right? This is also a simple event. And let me show you the counterpart of simple event. It's called compound event. we're going to mention this later on again. Compound event is a collection of all some simple events, two or more simple events. Now think about rolling a dice and then getting an even number. And we know that even number could be 2, 4, and 6. That being said, even getting an even number is not a simple event. It's a compound event. It has a component of 3 simple events here. Okay, so that's a difference between a simple event and compound event. Okay. But again, let's focus on the simple event for now, meaning it's an event or outcome that cannot be further broken down into simpler components. Okay. And sample space is basically the most simple word for the sample space is all possible outcomes. Meaning when you flip a coin, you get all possible outcomes. It will be head and tail, right? Head or tail, all possible outcomes. When you roll in a dice, those are all possible outcomes, right? Those are the possible outcomes. So the procedure consists of all possible simple events, all possible outcomes, right? So it consists of all the outcomes that cannot be broken down any further. Okay. So any questions so far? Event, simple event, sample space. Okay. Now think about this. We're using like a newborn baby case, right? When you go to a hospital, just randomly check a newborn baby, and you're gonna either have a baby boy or baby girl, right? So B represent a baby boy. Okay. From now on, anytime you see B, it means it represents baby boy, right? And you see G represent a baby girl. Let's explain what the event is, right? So for a single birth, meaning you check in one baby, you find out that it's a baby girl. So you have a one girl here. So this is a simple event, right? Definitely, a girl cannot be broken up further. And the sample space here, all possible outcomes either a boy or a girl. Now if you think about you checking 3 babies, now you're getting 2 boys and 1 girl. Okay. If you end up with the 2 boys and 1 girl, so you may have boy, boy, girl, right? Boy, girl, boy, or girl, boy, boy. 2 boys, 1 girl. Here the order matters, right? So in this particular case, we have 3 simple events. So this is what we call a compound event. Under this particular outcome, we could further broken down into 3 simple events: boy, boy, girl, boy, girl, boy, girl, boy, boy. And then the sample space is all the way from boy, 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 all the way to girl, girl, girl. All right, now I'm gonna show you a way to come up with this sample space. Think about this. When you look at 3 newborn babies, let's just focus on number of girls we can end up with. Okay. So start with the first outcome is 0 girl. That being said, 0 girl meaning they are all boys. So boy, boy, boy. Okay. So this is first category under the outcomes. Second category, you may have 1 girl. Now, out of 3 babies, there's 1 girl. Girl could be on the first spot. So girl, boy, boy, right? Girl could be on the second spot. So it's boy, girl, boy. Girl could be on the third spot. So it's boy, boy, girl. So by rearranging that girl on the first spot, meaning the oldest, the first one is a girl, second one is a girl, third one is a girl. Third major category will be 2 girls, right? If you look at 2 girls, now you only have 1 boy. So boy could be on the first spot, right? So boy, girl, girl. Boy could be on the second place. So girl, boy, girl. And boy could be on the third place. Girl, girl, boy. Okay. So now that's third category. And the fourth category is getting all 3 girls. Okay, then kind of be girl, 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 right? So here you start with the 3 boys all the way to 3 girls. And the middle one is 1 girls. And then you can actually match with this, right? This 3 matches with that. This 3 matches with that. And then boy, 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 first one, last one matched. And this is one way of looking at all these possible outcomes. And you could also focus on number of boys, right, being discovered in this process. You also will come up with the exact same outcomes. You can try that yourself. Maybe let's do this. I want you to try this, like what I did. Now focus on number of boys, right? And let's say 0 boy, 1 boy, 2 boy, 3 boys, right? See if you can come up with the outcome. Okay. All right, I'm gonna copy this. I'm gonna give you some time to analyze this yourself. I want you to list outcomes based on the focus on number of boys. See if they come up with the same result with that as well. So let me just share the screen with you. Now think about this. Okay, so 3 birds, right? Still 3 birds. Now focus on number of boys, right? First one is 0 boy. Second one will be 1 boy. Third outcome will be 2 boys. And then fourth outcome will be 3 boys. Okay, I want you to try this and then come up with all the possible outcomes yourself. Meanwhile, I'll take a look at attendance really quickly. Okay. Okay, so let's list all the outcomes. First one is 0 boy. 0 boy meaning all 3 of them must be girls, right? So girl, girl, girl. Okay. And second major category is 1 boy. So boy could be on the first place. So you get 1 boy, 2 girls. And then girl, boy, girl, second place. And then girl, girl, boy, right? If you look at 2 boys, that indicates there's 1 girl. So girl could be on the first place. So girl, boy, boy. Girl could be on the second place. Boy, girl, boy. And girl could be on the third place. Boy, boy, girl. Okay. And the last major category is 3 boys. So it has to be boy, boy, boy. And if you double check with the girl case, right? Remember the earlier time we compare this 0 girl, meaning all 3 boys. Okay. And second one, 1 girl. So gotta be girl, boy, 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 girl, boy, 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 girl. Okay, and third major category is two girls. So it will be boy, girl, 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 boy, girl, and then girl, girl, boy. Okay, and fourth one will be three girls, girl, girl, girl. As you can see, this matches, right? This matches. Now you see boy, girl, boy, girl, boy, girl, 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 boy. Same thing here. And then girl, boy, boy, girl, boy, boy. That matches. Okay. So this actually, if have zero boy, meaning has three girls, right? Three boys, meaning zero girls, same outcome. Two boys indicating one girls, equivalent outcomes. One boy equivalent to two girls. So just a couple of different ways of looking at all the possible outcomes we can generate from this process. And do you have any question on this? Okay. So now, again, this is about outcomes, right? All possible outcomes. We call this sample space. Okay. All right. Now let's move on to the next topic. So in terms of notation-wise, we're using P to represent the probability. Okay, capital letter P, right, represents probability, and then usually we use A, comma B, comma C, represents each specific event, right? So we could have a P of A denotes the probability of event A occurs. It could be probability of C, right? Indicates probability of event C occurs. Okay. Now this is just basic notations in terms of writing the probabilities. Let me just give you something a slightly richer flavor, A and B. So this event indicates probability of event A and event B occur at the same time, So if you write it as this special symbol is what we call A intercept B. So this is another type of a special event, which is indicating we want to find out common section of event A and event B, which means event A and event B occurs at the same time. Okay, and we're going to get to this argument later, right? When we talk about the addition rule and multiplication rules. Okay, now let's take a look. Remember, we have three different approaches of understanding, of understanding probability and then calculating the probability. Let's look at the first approach. The first approach is called relative frequency approximation of probability. So basically the procedure works like this. So you conduct the procedure, right? Or observe the procedure and count number of times event A actually occurs. Based on these actual results, probability of event A is approximated using number of times A occurs over number of times procedure was repeated. So think about this. Let's say you flip a coin 1,000 times. 1,000 times. And then count number of times heads show up. Heads turns up. And this is actually exactly the mirror of this procedure, right? Or this approach. So we observe this procedure, which is flipping a coin 1,000 times and counting number of heads turns up or shows up. And probability of head basically just equal to number of times. Yeah, I should use head. Probability of head equal to number of times has show up. That's occurred over number of times procedure is repeated. Procedure repeated. And actually, back in the ancient time, this is what the early mathematician was doing. So they basically just keep flipping a coin and eventually come up with this probability of heads and probability of tails. And that's why we are taking that for granted right now, because we know that probability of head got to be 50%, right? Probability of tail must be 50%, but it actually comes from the real life experience. So you have a 500 heads show up over 1,000 times. We flip a coin, then the probability turn out to be 50%. You can also write it, you write it as percentage, you could write it as decimal number 0.5, you could write it have half as a fraction. So several ways of writing the probabilities, right? It could be an exact fraction, exact percentage, or decimal numbers. Okay, they're all equally good. Okay, so this is the first approach. It's called relative frequency approach. And second approach is called classical approach of probability. And then this requires equally likely outcomes. So think about rolling a dice. Roll a dice. And we know that we have 6 outcomes, either 1, 2, 3, 4, 5, 6. Assuming this is fair dice, meaning it's not loaded, then either one of these outcomes has the same chance of occurring, meaning they are equally likely. Okay. So this procedure is assuming a given procedure has n different simple events, just like 6 different simple events. Each of those simple events has equal chance of occurring, equally likely, right? That's what it means. And event A could occur in S of these n ways, then probability of A equal S of n. Number of ways A could occur, number of different simple events. Now think about rolling a die and then getting an R number. I exactly mirror this procedure. Getting an R number could be 1, 3, or 5. Okay, so meaning getting an R number, this event has S different ways. In this case, will be 3 different ways, and out of total number of different simple events, which is 6. So here, probability of getting a R number, we know that there's 3 simple events embedded under the R numbers, so it will be 3. And then total simple events from the sample space, it's going to be 6. So it's 3 over 6. That turned out to be half. Again, you can also turn it into 50%. You can also turn it into 0.5. So this is exactly what this classical approach shows us, right? Okay, and then the third one, it's what we call the subjective probability. And let me give you an example first, and then you will understand why. Example could be weather forecast. This is exactly what we call a subjective probability, because it's never 100% accurate, right? If you look at a weather report, it's never 100% accurate because it's subjective. It's based on the professional knowledge about this previous, weather, or based on the what we know about current conditions, or make the best possible forecast. It could be an earthquake forecast. Again, it's never 100% accurate. It's not because people is doing sloppy job, or it just it's never possible to get a 100% accuracy on this kind of event, because the rationale behind this is they are using subjective probability. They just use the model, professional knowledge, to make the best possible prediction about the weather or earthquake. So probability of event A here is estimated by using knowledge of the relevant circumstances or professional knowledge. Okay. So also like forecasting about the economy, right? Economy forecast is never going to be 100% accurate, again, because it's just based on some professionals in the field. They come up with the best educated guess. So that's why you never come up with a 100% accurate result, right? Based on this subjective probability. But from the previous two approaches, like relative frequency approach and classical approach, you'll be able to get an accurate result, right? And a lot of probability was developed using the first two approach. So that's why we come up with certain things like probability of a head. When you flip a coin, probability of head has to be 50%. Probability of a tail must be 50%. It's based on one of this approach. Okay. And another important empirical experience is the law of large numbers, meaning if a procedure is repeated large number of times, or you can repeat again and again, and the relative frequency probability of event tends to approach the actual probability. So think about, flip a coin 10,000 times. And most likely you will get 5,000 heads, 5,000 tails. And we know that probability of head got to be 50%. This is essence behind the law of large numbers, meaning when you repeat this procedure many times, and your approximation becomes actual probability. Now we can use computer to do a simulation. So let a computer run a simulation, flipping coin maybe 1,000,000 times or 1,000,000,000 times, and then we can get a much more accurate, estimation, and that estimation becomes actual probability. So 0.5, right? Probability of tail also got to be 0.5. Okay. So this is a rationale behind the law of large numbers. And now, okay, and we talked about this already. When 3 children are born, the sample space is for all 3 boys, all the way 3 girls. Assuming the boys and girls are equally likely, find the probability of getting 3 children of the same gender. Okay. What do we mean by 3 children of the same gender? Basically says either we have 3 boys or we get 3 girls. And you can think about this, the 2 outcomes fit in this description, right? So probability of getting same gender, 2 outcomes satisfy the requirements to get 2 outcomes out of those 8 outcomes. So you divide into that, it's a quarter, right? Simplify that and get 0.25, also 25%. Okay. 3 outcomes, 3 probability, they're equally good, right? That means you have 20% of chance getting now 3 children of the same gender when 3 newborn babies are checked. Okay. Any question on this? Now think about this. How about let's find out what is probability of getting 2 boys and 1 girl. 2 boys, 1 girl. Okay. Any suggestion? Again, you can search through all these possible outcomes, right? So let's see which one satisfy this requirement. So this one, right? This is the first one, satisfy 2 boy, boy, girl. And this is the second one, boy, girl, boy. And then also girl, boy, boy. Okay, third one. So we have 3 outcomes, satisfy this requirement. So it will be 3/8. And this one we cannot simplify further, leave as the exact fraction, could be 0.375, right? Or you can also say it's 37.5%. Okay. And you can write it in 3 different ways: exact fraction, exact decimal, or exact percentage. Okay. All right, move forward. Simulation. I actually mentioned simulation a little bit. Nowadays, once we have a computer program, you can actually simulate any like event. Let's say we have a Mars explorations, and you want to find out, what's the chances of having a rare earth element in the Mars. And then you can use a computer simulation to achieve that goal. So you basically just let the computer run a simulation, same procedure, keep repeating that, and then eventually, we can come up with the probability of that event, right? By using a computer simulation. Also, you can use it to estimate the probability of getting, let's say, flip a coin, right? Probability getting head or tail. And matter of fact, you can use Excel to generate the outcomes. If you are interested in that, you can try research that. There's a way to do that in Excel. And you can just simulate the event of flipping a coin, and then keep repeating the process until you come up with a solid probability of a head or probability of tail. Okay. So this is simulation. Okay. Now let's take a look at probability limit. Okay, so probability is always expressed as a fraction of decimal numbers, or could be a percentage between 0 and 1. 0 is what we call the probability of impossible event. Let me give you an example of an impossible event, right? What is probability of Thanksgiving occurring on Wednesday? If you look at this, the outcome of this happening actually is 0, right? It's impossible, right? It's impossible for this to occur. We know that Thanksgiving always occurring on Thursday. So that brings us another, Thanksgiving occurring on Thursday. And this is what we call certain event. Certain event, probability of certain event is always 1. Probability of impossible event is 0. Okay. And any other event will occur in between. That's why the general conclusion is probability of event A, any event A, will be between greater equal to 0 and less equal to 1, right? So use interval notation to represent this probability of any event A. So between 0 and 1, 0 and 1 are included. Okay. And this is the boundary of the probability values. So if sometimes you see somebody writing as probability of event A equal to 1.2, right? And we immediately know that this is wrong statement. Probability of event A can never be 1.2 because it's just impossible. This is also what we call an impossible event. Right? Or probability of event A, or probability of event A equal to negative 0.2. Right? It's never happening. It's impossible. And just give you an idea, what the probability value could be, right? And the probability limits. And this is a breakdown of all these different type of events. We could have a certain event, meaning probability of that event equal to 8 to 1. And we could have a likely event. Think about 0.75, all the way to 1, right? And between 0.75 and 1, or somewhere around that's a likely event. And all these ranges here could be a likely event. Okay. About 50% all the way to 1, right? That's likely event. And we have 0.5 as middleman, 50% of chance. Meaning it's 0.5, you get half and half, right? 50-50 chance. And anything between 0 and 0.5, that's what we call the unlikely event. Okay. And impossible event will be probability equal to 0. So let's just give you some idea how to interpret this, the value of the probability. So for example, if you have a probability of event A equal 0.6, I will say that this will be a likely event. If let's say a probability of event B equal to 0.2, you will say that it is probably unlikely event. And that's how you distinguish different level of certainty, right, over the spectrum, and help you understand what the value means. Okay. Now, another important concept in this probability field is called complementary events. So the complement of event A, we use this notation A bar, or A with a horizontal line on top of it is called a complement event. So A bar here represent complement event of event A. Okay. This is the meaning of this. And basically consists of all outcomes in which event A does not occur. So it's either A or not A. So this also, you can interpret this not A. That's an essential meaning of complement event of event A. So for any event or any procedure you look at, you can always categorize that into A and not A, right? Could be so think about rolling a dice, right? And you want to get a 6. So your focus is getting a 6. Now, all you focus on is either 6 or not 6. Right? Let's say you're betting against somebody else. If you rolling a dice, you get a 6, then you win some money. Then that means you want to focus on getting a 6, right? And everything else, it's irrelevant for you. It's not important. So a lot of this works similarly like the casino business, right? If you go to a casino, if you're betting on certain numbers, you want that number to show up, right? Or you go to slot machine, you want specific combinations show up so you can win money. And so all the event becomes 2 categories, either winning numbers or not winning numbers, right? Or losing numbers. So they are counterparts of each other. Okay. So this help you understand what is complementary event. Okay. And let's think about this. Right? Let's say 1,010 United States adults were surveyed, and 202 of them were smokers. So let's say, what is probability of smokers? So using number of smokers, 202 over total adults surveyed, right? So 10, 10. So this turned out to be 2 over 10, or 1 over 5, right? If you simplify further, and that becomes 0.2. That could be 20%. And then you don't have to write all three outcomes, right? If you prefer decimal numbers, just write the decimal number. And a lot of professional research, or like publications, you see probability usually expressed in terms of decimal or percentage, right? And what if we want to know what is probability of non-smoker? Meaning not A. This is event A. Event A here is smoker. Then not A means non-smoker. Okay, it's exactly the opposite side, right? Or you can call counterparty, non-smokers. And we know that we have 808 non-smokers over 1010. And this turned out to be over 10, which is 4 over 5. And this is 0.8. You can also say that it's 80%. If you look at it, when you combine these two, you get 100%. Because the total probability has to be 100% for any event. Okay. Or you can also just write the probability non-smoker using 1 minus probability of smokers. So 100% minus 20% also gives us 80%. Okay. This is another way of looking at this. But I'll just show you, what this, how this complementary event plays out. Okay. Any question on this? So when expressing the value of probability, either give the exact fraction, decimal, or run a final decimal result to 3 significant digits. For example, if let's say you have a probability of event A that turned out to be 1 over 3, right? 1/3 of chance. And we know that it's going to be 0.333, right? Lasts forever. And when that happens, you run it 3 significant digits, meaning you run to the 3rd decimal place, underline digit, and you look at critical digit, it's less than 5, then we know that this must be written as 0.333. Okay. And yeah, that's how you basically follow this. So either fraction, decimal, percentage, whichever you prefer. But if it is in the case of not a perfect answer, not perfect decimal answers, then the running rules is run to 3 significant digits, just like what we did, right? All right. Any questions so far? Okay. So events unlikely if the probability is very small, and unlikely definition is 0.05 or less. So the probability of event A is less equal to 0.05. That means this is what we call highly unlikely event. Unlikely event. Okay. So that being said, an event has usually low numbers of outcomes of particular type, or unusually high number of those outcomes, that this number is far from what we typically expect. So this is all highly unlikely, right? So think about this. Remember, flip a coin, let's say flip coin 1,000 times. And you come up with this first outcome is you come up with 100 heads. Remember, we expect to have 500 heads. However, in this particular simulation, you come out with 100 heads, and this is very low number, right? And that deviates from our expectation. We expect to have 500 heads, but only 100 shows up. And this unusually low numbers indicates this is highly unlikely event. It's unlikely. If that happens, meaning It's like chance of winning lottery, right? Highly unlikely. Yeah. A second outcome could be, let's say you get 900 heads. And that's also highly unlikely, right? We expect to have 500 heads. However, 900 heads show up, and we know that this is unlikely. Just deviate from the common sense or the convention, and we call this unlikely events. Okay. Yeah, this is pretty much everything from section 4.1. And let's take a look at section 4.2. Okay. I'm going to take a look at addition rules. Okay. The screen video. Now, second important topic in this chapter is what we call the addition rules. And the notation here is what we call probability A or B. So we have two events, event A and event B. And this A or B indicates probability of A union B. That means everything in A, everything in B, so three different layers. And everything in A intercept B, meaning both A and B, everything in the case in the case of A and B occurring at the same time. Together. So three different, elements included in this A or B, right? And this is what we call addition rules. We're adding these two events together. So this section presents the addition rule as this, and just try to elaborate it earlier. As a device for finding probability that could be expressed as PA or B, right? And more precise, mathematical notation will be probability A union B. This U symbol indicates union. So meaning including everything A, everything B, everything of that intercept, meaning both event A and event B occurs at the same time, right? Three layers, event A occurs, event B occurs, or they both occur at the same time. Okay. And this is essence of the addition rules. And I start with this notation, right? P, probability of A or B. And then that brings us to a compound event. We know that A or B is a compound event, right? And any event combining two or more simple events. I already bring up a example, right? When you're rolling a dice, getting an odd number, this is exactly a compound event, right? Because it has three simple events, which is getting a 1, getting a 3, getting a 5. Okay. A or B is notation, event A occurs, event B occurs, or they both occur in a single trial. Okay. So this is how you approach this notation. And now, once you find the probability that event A occurs, event B occurs, find the total number of ways A could occur and the total number of ways B could occur. And you also think about this. So this is event A. I use a circle to represent event A. All right, and then using a circle to represent event B. assuming they have a common section. So you're going to include everything in A. I'm going to use a different color to help you visualize this. We're going to include everything here in A, right? We're going to also including everything here in B. Okay. And we're also going to include common section of A and B, meaning they A and B occurs at the same time, but without double counting this common section. So no double counting. And this is very important, right? Because even A and even B could occur at the same time. And if you're just adding probability, so if you're just adding A or B, just simply adding probability of A plus probability of B, you may be double counting the common section here twice, right? So typically we will, if they have a common section, they could occur at the same time, then we subtracted A into the B, meaning both A and B occur at the same time. So this is how we handle this when this particular case it's going on. Okay. So here we go. Formal addition rule is probability A or B equal probability A plus probability B. And then when you just adding those, when they have common section, we are counting the common section twice, right? Because this green section will be counted twice. And we need to subtract once. So subtract probability A and B. So if you want to write it as a mathematical notation, it will be A union B will be equal to probability of A plus probability of B minus probability of A intercept B. Okay, the intersection, meaning both events occur at the same time. Okay, so A and B here is what we call the both A and even B occur at the same time. Okay. Now think about the intuitive rules. I'm gonna bring to this notion called Venn diagram. Assuming we have a rectangle box, okay. And then within the rectangle box, we have two events. Event A goes here, and we also have event B goes here. Okay. And intuitive addition rule basically tells us that if you want to combine event A and event B, A union B, both events together, so you're going to do probability of event A plus probability of event B. Okay. I'm using different color to represent each region. So here, this region, it's in A, but not in B, right? Everything in A, but not in B. And also we're gonna add in this. So this, maybe use the same color. Right here, this is everything in A, right? In the blue color. Everything in B, I'm gonna use a different color, purple. Okay, so in B is purple color. And also this part. So by just adding those two, we double counting the common section or the intercept. Intercept was counting twice. So obviously this won't be the correct result. So that's why we need to subtract it once. Okay, now we come up with this intuitive addition rules, right? By drawing this Venn diagram and try to visualize this. Okay. And we have two different scenarios. First one is we have disjoint event or mutually exclusive. Think about event A and event B are disjoint or mutually exclusive if they cannot occur at the same time. So think about this, the second Venn diagram here. You see this is probability event A, probability event B. And since they are mutually exclusive, they are disjoint, so they do not have intersection. So here for this mutually exclusive, and the addition rule will be written as A or B, or probability of A in union B. It just becomes probability of A plus probability of B. Because there's no intersection, so intersection is 0, right? No intersection equals 0. Note that probability of A intercept B equals 0. Okay. That's how this goes. And this one is not joined, not disjoint. We call this join event. And this is more common case because two events usually have some connection with each other. So that's why we call this join event. And we focus more on join event because slightly more complicated. And it's more interesting in terms of understanding this probability. Okay. Now think about this. And let's look at this example. In math class of 30 students, 17 are boys and 13 are girls. On a particular unit test, 4 boys and 5 girls made A grade, right? If a student is chosen at random from the class, what is probability of chosen girl or an A student? Okay. Now I want you to think about this, right? And then I'll give you a couple minutes. Think about this, see if you can figure out the probability. And the hint is we are using addition rule here. Nice. Okay. You can also try to draw a Venn diagram, see how this works out. Okay, so let me show you the solution, right? So if you just apply the addition rule, we are talking about probability of a girl or a student, right? Either one of these, and applying the addition rule, it should be written as a student. Probability of a girl plus probability of a student. And you're going to subtract the common section, girl and a student at the same time. Because they have intersection. So you look at the probability of girl is 13 out of 30. You look at probability of the A student, right? We have 4 boys and 5 girls are A students, so it's 9 total A students over 30. However, there are 5 girls who made an A grade, meaning that's a common section of girl and A student. Then we're going to subtract 5 over 30. So the final result should be 22, right? 13 plus 9 is 22 minus 5, 17 over 30. They're going to show in the Venn diagram. Okay. So we have 2 event, girl, A grade, right? We know that the common section, 5 girls made A grade. And if 5 girls made A grade, the rest of the girl made the other grade. So 13 minus 5, that's 8 girls who made other grade. And there are a total of 9 A students, right? 4 boys and 5 girls, then 4 is here. So if you're adding all those up, A plus 5 plus 4, that's also 17. Okay. Total 17. Okay. And then 17 over 30 will be the probability. But that's how you split it up into different like components using the Venn diagram. Okay. But same result, right? By using the formula directly or break down into different elements and combine total. Now think about this. A single 6-sided die is rolled with the probability of rolling a number greater than 3 and an even number. Okay, again, I'm gonna give you a couple minutes. Think about this. Using addition rule, right? So try to use addition rule. All right, so let's quickly look at the result. Here, probability, we look at two events. First event is greater than 3. And second event is an even number. So either one of that. So all even number. So we can look at it as probability of 3 for the greater than 3. Getting a number which is greater than 3 plus probability of even number. We look at these two events, they have intercept, right? So greater than 3 could be 4, 5, 6. Even number could be 2, 4, 6. So greater than 3, 4, 5, 6, right? Even number is 2, 4, 6. So that's the intercept here. 4 and 6 are the intercept. So that means we double counting these two numbers. So we get a subtract greater than 3. Intercept and even number. So greater than 3, we know that it's 3 out of 6 number. And even number 3 over 6. That's not a right answer, right? It's probability is not 100% here because these two event has intercept. Intercept is 4 and 6. So you subtract the intercept, 2 over 6. And you end up with a 6 minus 2, which is 4 over 6. And that's turned out to be 2/3. Okay, so probability of this event actually is 2/3. You can also draw a Venn diagram, visualize this. First event is greater than 3. And second one is even number. We know that common section is 4, 6, right? Right here, 4, 6. Greater than 3 is 4, 5, 6. 5 goes here. Even number is 2, 4, 6. So if you're counting all these numbers, only 4 numbers, right? 2, 4, 5, 6. 4 numbers satisfy both events. So that's why it's 4 over 6. And it's 2/3. And this Venn diagram, if you want to look at what's outside of this, will be 1 and 3. Right, 1 and 3 is outside these two circles. So that will complete the entire, sample space, right? So 1, 2, 3, 4, 5, 6. Okay. All right, so this is a second example on this. Now let's take a look at complementary events. So event A and then A bar. A bar is a complement event, must be disjoint or mutually exclusive, right? Because it's either A or not A. Okay, complement event. They are mutually exclusive, either A or not A. So it's impossible for event and its complement event to occur at the same time. That's what we mean by mutually exclusive or disjoint. Okay. So if you draw this Venn diagram, this is A, and this one is not A, or A bar, right? Whichever you want to write it. And they do not have a common, right? They are disjoint. Okay. Now, rule of complement events is probability of A plus probability of complement event A equal to 1. So if you want to solve for probability of complement event A, just using total probability 1 minus probability of event A, and vice versa, right? Probability of event A equals 1 minus probability of complement of event A. Okay. So this is total area is 1, and the yellow circle in the middle is probability of event A, and then everything outside of the circle is complement of event A, and together they becomes total area 1. So that's how you look at event A and then complement of event A. Now, one more time, look at this. A number is chosen at random from a set of whole numbers from 1 to 50. Okay, you have here, we have 50 numbers. The way how you counting how many total numbers in between, with 50 minus 1, ending number minus beginning number, adding 1. Because we are including the very first number, so we assuming we have 50 numbers here. Okay. And you want to calculate the probability that chosen number is not a perfect square. Okay. All right. Not a perfect square, meaning the counterparty is a perfect square. So you want to find out that first, and then they will be able to find out not a perfect square, right? So I want you to quickly try this question, and we'll talk about it in a second. All right, let's take a look at solution here. So you have two parties involved here, perfect squares. And not perfect squares. If you look at perfect square, we can start with the 1 square, right? That's 1. And 2 square, that's 4. And 3 square, 9. So we're getting organized. We start with the lowest number all the way increasing. And 4 square, that's 16. And 5 square, that's 25. 6 square is 36. 7 square is 49, right? We cannot go beyond that because a square is 64. It's out of the range. So we do not consider that. So you're counting how many perfect square here. You get a 1, 2, 3, 4, 5, 6, 7. Meaning we have 7 perfect squares. So if you do not want to list all not perfect squares, it has to be 50 minus 7, which is 43. So in this case, it will be a little bit easier to just count the perfect squares, because we only have 7 perfect squares compared to not perfect square. I have 43 of them, and it would take a while to write out all those 43 numbers. So then we know that probability of not perfect square, using complementary event, rules, will be 1 minus probability of perfect square. Then we know that there are 7 perfect squares. So it's going to be 1 minus 7 over 50. And this is 43 over 50. Okay. You can leave it as exact fraction, or you can write it as decimal number 0.86. Right. If we divide into that, we know that it's 0.86. That means out of all 50 numbers here, 86% of them are not perfect squares. Any question on this? Yep, that's pretty much everything on the section 4.2 about addition rule. And let's go back. We have some time left. Let's go back to the textbook. And then let's take a look at any question in the back of the textbook, which is interesting. And we can look at those as well. And let's go to the, open the textbook. Okay, let's get to section 4.1 in the textbook. It should be about 150, right? Go to index page. No, not 150, it's 120 probably. Yeah, it's 3.4, then let's get to 4.1. Okay, so you look at all these numbers, I think it's pretty, okay. We toss a fair coin 3 times. How many outcomes do we have? Okay, let's look at tossing a coin 3 times. Okay, and let me explain that using let me show you another method to construct a sample space or look at the outcomes. All right, think about toss a coin 3 times. And find the sample space. Okay. And here I'm going to show you a method called tree diagram. Obviously, you can use the method I showed you earlier, right? Look at how many heads you will search for, right? And you can have a 0 head, 1 head, 2 head, 3 heads. Focus on one of the major outcomes and come up with all the outcomes, right? All the possible outcomes here. We call it sample space. And the tree diagram works like this. So we have a starting point here. Okay, starts here. If you look at the first, when we toss the coin first time, remember we have 2 outcomes, either a head or tail. H represent head, T represent tail. 2 outcomes, right? And flip it second times. Still, we only have 2 outcomes, either head or tail, right? Head or tail. Now you flip it 3rd times. Still, outcomes are constant, right? You gotta either have a head or tail, nothing else. Head or tail. Head or tail. And it's like all of this is like a branch of the tree, but it's a little bit upside down, right? And based on this branch of trees, and you'll be able to come up with all the possible outcomes here. So the first outcome will be follow the branch of the tree, right? Here, here. 3 heads. Head, head, head. Triple heads. So 3 heads. Second branch is head, head, tail. Third branch, head, tail, head. And then 4th branch is head, tail, tail. And this is the first half of the branch, right? If you look at it, first half. Second half, start with the tail, tail, head, head. And second outcome, second branch, tail, head, tail. And second to last outcome is tail, tail, head. And the very last outcome is all tails. If you look at this, we have 8 possible outcomes here, right? First half is 4 outcomes, second half 4 outcomes. So total 8 outcomes. Okay. Now just using the method we talked about earlier in the section 4.1, if you focus on the major branches of outcomes, right, you could have 0 head. Well, let's do 3 heads first to match with these outcomes here. So I'll do 3 heads first. And 2 heads, 1 head, and 0 head. Three heads. Just focus on number of heads possible here. So it'll be head, head, head. Now focus on 2 heads. 2 heads indicating 1 tails. So now we're going to relocate the tail. Tail on the first spot, right? Tail, head. Now, to match exact this. Okay, it's okay. So tail, head, head. So tail on the first place. Now tail could be on the second place. Head, tail, head. Tail on the third place. Head, head, tail. Okay. 2 heads. Third major branches. 1 head. So that will be head on the first place, head, tail, tail. Head on the second place, tail, head, tail. And then head on the third place, tail, tail, head. Okay. And then the very last outcome will be 0 head. 0 head meaning 3 tails. Okay. 3 tails or all tails. If you combine all this, total A outcomes, right? Exact same result. So now we have 2 different ways of looking at this problem, this type of problem. Anything is binary, right? If you look at this is binary outcomes, like head and tail, boy, girl, right? And then also anything like binary, right? Like all those, the foundation of the computer system, right? It's 0, 1, right? That's also binary. So either each outcome decision is determined either by 0 or 1. When these binary outcomes, and then one way to look at it is we have 3 spots here. First spot, first flip the coin first time, right? Flip the coin second time, flip the coin third time. And when you flip the coin first time, 2 outcomes, right? When you flip it second time, still 2 outcomes. Third time, 2 outcomes. And they are independent. So if you multiply across, it turns out to be 2 to the 3rd power. So this turned out to be 8. Now, similarly speaking, what if you flip a coin 4 times? What is the sample space? If we just want to know how many outcomes are there without looking into the details, anybody get an idea? When you flip a coin 4 times, how many possible outcomes are there?
Would it be 16?
Exactly. Very good. How do you get 16?
Because here you had like 3 over 2, actually. I don't know exactly how to say that. So it would be 2 and 4. I don't know. I just multiplied 8 again by 2.
Okay. I think that's a great answer, Alexandra. Yeah, that's totally right. Actually, you can just look at it like what I just present here. You know, we're gonna flip it 4 times, right? You can just draw a rectangle box like this. And this is the first time you flip it, second time you flip it, third time, 4th times. Okay. Now on each trial, every time you flip it, remember we only have 2 outcomes. 2 outcomes, right? That does not change. This is constant. And since they are independent, meaning getting ahead on the first trial does not guarantee anything, right? You can get ahead on the second trial. You can get a tail on the second trial. So this does not guarantee anything. So you just multiply across. So meaning they are independent. Independent is very important concept here. In order to apply this multiplication rule, so it's 2 to the 4th power. Okay, and that will be 16. Yeah, exactly what you just described. And that's how you end up with this. And what if you want all the detailed outcomes? Then you can draw a tree diagram, right? Just like what I did here. Although this one is slightly more complicated because when you flip a coin more frequently, then the sample space gets larger. And since it's larger sample space, it's harder to summarize all the samples, all the possible outcomes. Think about if you flip a coin 10 times, 20 times, now sample space is humongous, right? So it wouldn't be wise to do it by hand. Usually we use a computer simulation or computer system to generate all outcomes here. But that's just something, you know, it's out of topic. You know, we're not going to get into the much more complicated case because this is, again, it's intro to probability. We're not going to go too deep into the subject. So if you understand what we talk about in the class, you should be fine, right? Okay. And let's see anything else in there. So it's pretty normal, right? A die is rolled and a number that come up is recorded. And again, you know, we're talking about 6-face die here, right? Very standard ones. The second one already explained it to you, and then you can come up. We already have all the outcomes listed, and you can look at it yourself. It shouldn't be a problem. And you toss a coin 7 times. And I will go over this one. This one is interesting. So you toss a coin 7 times. Okay, what is probability then? No more than 6 heads come up. Okay. This one is slightly more complicated, so I will go over this. So that's a, and what we talked about earlier is it's useful, right? In the previous section. So now toss coin 7 times, probability of no more than 6 heads. No more than 6 indicates what is the so think about this, no more than 6 heads, the counterparty, right? The complementary event will be more than 6 heads, right? Okay. More than 6 heads, gotta be 7 heads. Meaning you get this outcome. All heads, right? And it's only one possible outcomes under this assumption. So now if you think about toss a coin 7 times, all right, so we need 7 rectangle box here. 1, 2, 3, 4, 5, 6, 7. First time you toss the coin, second time you toss it, third time, fourth time, fifth, sixth, and seventh. So this one is like combine the complementary event with this sample space. Okay. So first, when you toss it first time, you get 2 outcomes. Second time, you get 2 outcomes. Third time, you get 2 outcomes, 2 outcomes, 2 outcomes. It's again, it's binary system. And you multiply across, you get 2 to the 7th power. And 2 to the 7th is 128. So meaning we have 120 outcomes. And out of these 120 outcomes, only one outcome satisfies the complement event, right? Which is 1. So that means no more than 6 heads has 128 minus 1. So 127 outcomes satisfy no more than 6 heads. So if you look at the probability of this event, it should be probability of no more than 6 heads is equal to 1 minus complement of this. Complement of this is more than 6 heads. Then we already analyze it. It has to be 7 heads. It's 1 minus probability of 7 heads. And we know that only one outcome satisfies 7 heads. So it got to be 1 over 128, right? And the result has to be 127 over 128. Okay, so we're using complementary event concept to tackle this. It's a lot easier doing this. If you just go and counting how many outcomes in no more than 6 heads, it will take a long time, right? Really long time to get all these 127 outcomes. So by using the complementary events, that helps a lot, right? Help you understand this a lot better. Okay, and this one is a challenge one in your homework assignment. So I'm gonna go over that with you. And let's go to a section, second section, and see anything interesting there. Okay. The rest of them you could to complete it, right? It's not that complicated. And second one is about expected values. We haven't talked about expected values, so I guess that's fine. By the time we get to the expected values, we can talk about it. And the rationale behind this is it's quite simple. And we're gonna talk about it in a bit, right? When you get to section, the last section of the chapter on 4.5, we're going to talk about expected values. Then we will take a look at all these different, examples in your textbook. Okay. All right. I guess I will stop here today. Do you have any question with respect to what we learned today? Okay. Then in that case, I will talk to you guys on Friday, and we can talk about I'll give you some feedbacks on your Excel project 4 and 5, and also if you need feedbacks on your test number 2, I can also do that. So I'll give you a chance to revise your project number 4 and 5 if you did not get a perfect score on Friday. Okay, I guess that's it. I'll talk to you guys on Friday.
Thank you.
No problem, guys. Bye-bye.